Welcome again to lectures in the subject State Space Approach to Control System Analysis and Design. The topic for discussion in this video is numerical solution of state equations. Earlier we have solved state equations analytically and we observed, of course the discussion was limited to time invariant systems, and we observed that obtaining analytical solutions is a complicated task. It is required to utilize numerical methods to solving the state equations, which is quite natural due to the availability of widespread availability and access to computers. There are few advantages offered by numerical simulation. Numerical methods are capable of solving linear as well as nonlinear equations. They can also handle time varying cases. And solution to nonlinear state equations helps verify the acceptability of designs obtained using linear models. This I will elaborate a little. Generally, whenever we model a physical system, in most of the situations we get nonlinear model. So around the operating point or around the equilibrium, we linearize the nonlinear mathematical model, and thereby we convert a nonlinear model to a linear model. Based on the linear model, generally we design a controller or a state estimator, and then the parameters of the controller or the controller along with parameters and structure is to be implemented back on the nonlinear plant or the system. Similarly, the nonlinear states are to be estimated using an estimator which is essentially a linear estimator. Now there has to be a confidence that a linear design will work for the nonlinear system. So what we do, we simulate the nonlinear state equations, and on that we verify the designs obtained using the linear models. It builds our confidence. Now in this video, in this lecture, we will briefly see a few numerical methods for solving the nonlinear state equation represented as x dot at time t equal to a nonlinear function f of the state x at time t and the input at time t. And initial condition given is the state is known at the time t equal to t0, which is initial time, and the input is known for the time t at and beyond t0. And with this we have to solve this differential equation. Now in mathematical literature these are known as initial value problems, and quite a few numerical methods of solution are available. From that we will study three of the methods. One is Euler's method or Euler's explicit method, other is Euler's implicit method, and we will also see Runge-Kutta method. So we first see the Euler's method. The derivative dx by dt or x dot is represented by this: x at the time step tk plus 1 minus x the state at the previous time step tk. Tk and tk plus 1 are separated by a small interval delta tk k plus 1. So the difference of the values of the state at the two time instants, the two consecutive time instants, divided by the delta t is basically the approximation to the derivative or the function. This left hand side was the derivative, right hand side was the function. This derivative is approximated by this difference in values of states at the two time instants divided by the delta t, the separation between the time instant. This is the value of the function evaluated at time t equal to tk, the initial time. This is essentially what is done in the Euler's explicit method. Now this can be manipulated and we can obtain solution for xtk, which will be equal to the x at tk, the previous time, plus delta t into the function evaluated at t equal to tk. From this we can see that because we are given at t0 the value of xt as xt0 and value of ut is given, so by substituting the values of xt0 and here the value of xt0 and ut0, we can evaluate f, multiply that to delta t, and we can obtain the solution xt1. Having obtained xt1, and we will know the input is given at instant t1, so from knowledge of ut1 and from the computed value or numerically solved value xt1, one can obtain x at time instant t2. And in this manner one can obtain xt3, xt4, etc. Thus, in many repeated evaluations, we will get the required solution. This is the Euler's explicit method. Now, when we apply this to a linear system, which is represented by a coefficient matrix A, which may or may not vary with time, and input matrix B, so we get this. We get A at instant tk and B at instant tk. Of course, xtk and utk have to be there. And left hand side is identical as was in the nonlinear case. So if we manipulate this, then we get xtk plus 1 minus xtk equal to this delta tk multiplies to the right side. A at instant tk multiplied by delta t into x plus b into delta t into the input. And then we do further manipulation by taking xtk on the right side and taking xtk common on the right. We get this thing in the identity matrix plus atk into delta tk multiplies to the xtk plus btk delta tk into uk. So in this manner, once we build this matrix, we have the solution of xtk. For example, given x0 and u0, we will get x1. Given the solution x1, we plug here, and u1, we will get xt2 and so on. So in this manner we can do the repeated application of this equation and get the solution at various time instant t1, t2, etc. Now what we observe is that this quantity in brackets here is approximation of the state transition matrix evaluated for tk plus 1. As we have seen, phi tk plus 1 will be equal to e power a tk plus 1. So basically e power a delta t, and which is expressed by this series: identity matrix plus a into delta t plus half a square delta t square plus 1 by factorial 3 a cube delta t cube, etc. So if we ignore second order and higher order terms, we are left with this, which is this. So Euler's method is essentially, in case of linear system, approximation of this state transition matrix by ignoring the second and higher order terms. Euler's method or Euler's explicit method is prone to numerical instability and requires small time steps for solution. Numerical instability problem can be overcome by deploying the Euler's implicit method. Essentially, in the Euler's implicit method, left hand side is same as that in the explicit method. However, the right hand side you can see the function is evaluated now tk plus 1, input is utilized at tk plus 1, and in the Euler's explicit method here we had tk and uk. So the derivative is to be evaluated at the end of the time step rather than the start of the time step, which was done in Euler's explicit method. If we manipulate this, we get this, and we have to of course obtain the expression for x tk plus 1. We have to derive it analytically, and then iterative solution can be performed. So Euler's implicit method is little difficult to apply. However, it tolerates larger time step and it is numerically stable. So in case of linear systems, the representation is like this. Right hand side is matrix multiplied by the state plus input matrix multiplied by the input, both taken at the end of the time step, that tk plus 1. Manipulating this is basically we are multiplying this to the terms on the right. So left hand side becomes this difference of the values of state at the two consecutive time steps tk plus 1 and tk. A evaluated at tk plus 1 and delta t between the two time instants plus b into delta t between the two time instants and the value of input at the end of the time step. When we simplify this, we get x tk plus 1 as identity matrix minus the A matrix and then inverse of that. Essentially we take this term on the left, this term on the right, and then we take this common and multiply by its inverse on both the sides. So we get this expression. So we have to evaluate identity minus A into delta t and its inverse, then we can obtain the xtk by the repeated solution. So we can see the complexity involved compared to the Euler's method, where we did not have inversion of the matrix. In the Runge-Kutta method, again, this is the equation to be solved, just a repeat of the problem. And here the solution is expressed by this expression. X tk plus 1, the value of the state at the end of the time step, is equal to value of the state at the beginning of the time step plus delta t divided by 6. Please note this 6 is sum of 1 plus 2 plus 2 plus 1 divided by 6 plus the value of the function evaluated at the initial time, start of the time step, at the end of the time step, and at the middle of the time step twice. So this is the evaluation of the function. We know the value of the state at time tk and the value of the input at time tk. Using those values, we can evaluate the function at the start of the time step. Now using this, here please see, we essentially this is the value of the state evaluated using this slope, this derivative at the middle of the time step. And of course the input value is to be utilized as given at the middle of the time step. So that gives the value of the function at the middle of the time step. Once again the value of the function is evaluated at the middle of the time step, utilizing the value of the state computed using this slope. This the value of the function at the middle of the time step, and similarly the value of the input at the middle of the time step. And finally the value of the function or the derivative essentially is computed at the end of the time step by using the value of the state at the beginning of the time step plus the change in the state estimated using the value of the derivative at the middle of the time step. So in this manner we obtain the value of the derivative 4 times, once at the start of the time step, once at the end of the time step, and twice at the middle of the time step. And we give more weightage to the value of the function or the derivative at the middle of the time step, and we obtain this weighted average ds plus 2dm1 plus 2dm2 plus de divided by 6, and that we multiply with delta t between time instants tk and tk plus 1, and then we evaluate xtk. In this manner, using this expression, a repeated application of this, we can solve the given system of first order differential equations or the state equations to obtain the solution. The Runge-Kutta method, it has been observed that it can work with larger values of time step than the Euler's methods, both explicit and implicit. Now there is an exercise for you. This system is there. Please note that this is a nonlinear system. The state x1 is multiplying to input. The B matrix contains s1. A is of course constant matrix. So given this system representation and given the initial condition like this, solve the response for unit step input. Ut is 1 for t greater than equal to 0. We have to solve for x1 using the Euler's both the methods, the explicit and the implicit methods, and the Runge-Kutta method. And what you have to do is you have to obtain the time series, the value of the states x1, x2, the derivatives x1 dot and x2 dot at different instants of time is spaced by 0.05. So 0, 0.05, 0.1, 0.15, 0.2, etc. Of course, one can also solve this equation analytically. To do that, what we utilize is that when input is 1, then this state equation can be simplified as x dot equal to minus 5.1 6 minus 0.1 x, because this 1 into x1 merges in this part and then this coefficient changes, becomes minus 5, and this is like an autonomous equation which can be solved, and most likely you will get this solution. And using this analytical solution, one can evaluate the value at t equal to 0.25 and t equal to 0.5 and compare the numerically obtained values with these values to see that what is the kind of accuracy, what is the typical accuracy being provided by Euler's methods and the Runge-Kutta method. One can do this exercise to understand the three methods in a greater detail. Now we come, if we have linear time invariant model, then their solution can be even more fast. It can be simpler if it is discretized. and this is shown in the next few slides and this slide. We are given with the linear time invariant model x dot equal to ax plus bu. A and b are constant matrices, and the initial state is given and the input is given for time t greater than equal to 0. So its solution, we have seen analytically, its solution is this. In earlier lectures we have seen this solution. Now what we do is we consider two time instants tk and tk plus 1 separated by delta tk k plus 1. The values of state at tk is xk and the value of state at tk plus 1 is xtk plus 1. We can obtain by substituting t equal to tk the expression for xtk, which is this. We can also obtain the expression for xtk plus 1 by substituting t equal to tk plus 1 again in the same equation, which comes as this. Now we pre-multiply this equation by e power a delta t, and this is e power a delta t is this tk plus 1 minus tk, and subtract from this xtk plus 1. So left hand side is xtk plus 1 minus e a power delta t between the two time instants into xtk, which is this thing minus this thing. So this thing minus e power a into delta t multiplied by this integral, and that e power a into delta t, when it adds to e power a into tk, it gives e power a tk plus 1 here. And we can simplify that. Before that, what we do is we break this integral into two, one from t0 to tk and other from tk to tk plus 1. This, it is done here, shown in this square brackets. This is the first part and this is the second part. And we can see that this part cancels with this part, and what remains is this and this, which is reproduced here. Then there is we do manipulation by using a change of variable. Tk plus 1 minus tau is represented as mu. So d tau will become minus d mu, and the limits of integral will change to this. Also we assume, because we are discretizing, we assume that the input is constant over the small interval between tk and tk plus 1. It is constant at its value at tk. So which is this utk. We assume that it doesn't vary during the small interval tk and tk plus 1. Then we get this solution. xtk plus 1 is given as e power a into delta t between tk and tk plus 1 into xtk plus this integral. So it can be rewritten that e power a delta t is written as phi delta t. So that multiplies to the value of state at the start of the time step, and this gamma, which is this integral, multiplies the value of input at the start of the time step. And so x take e plus 1, the next value of state, is obtained by recursive application of this. So the advantage of this formulation is that we can evaluate phi t and gamma t once, and then repeated application of this equation will give x at t1, x at t2 and so on. Of course, if the time interval is constant, if the sampling is being done at uniform rate, then only it will happen. If the sampling is non-uniform, then we have to evaluate using this expression. Generally, we have uniform sampling, so phi t and gamma t are evaluated once, and so state x is solved by iteration using this expression. So it becomes computationally more efficient. We summarize: the numerical methods for solution of first order differential equations may be used for solving the state equations because they are advantageous compared to analytical methods. Euler's method is the simplest in implementation, especially the Euler's explicit method. However, it requires small time steps for stability of computation and for achieving good accuracy, accurate solutions. Runge-Kutta method is known to work with relatively larger values of time step than the Euler's methods. Hence, even though it is computationally more demanding, more complex compared to Euler's method, it can be efficient in simulations in most of the situations. The response of linear time invariant systems can be obtained recursively by discretization very efficiently based on the discretization. So with that we complete this lecture also. See you again in the next lecture. Thank you very much.